Hello, my name is Crystal Parker and I'll be presenting raycasting video games as my final project for Matrix Theory and Linear Algebra Winter 2021. So, what is raycasting? Raycasting became a big deal in 1992 because of Wolfenstein 3D, a pseudo 3D game. Before that, there were no 3D games. The idea is that by tracing imaginary rays from the player's location on a 2D map, you can create a 3D projection in the player's viewpoint. What are these imaginary rays and what information do we get from them to make a 3D world? To summarize, they are vectors, and using them in a 2D map, we can calculate line intersections, and using the length of the line to the intersection, we can determine how big our walls will appear on the screen. In this image, you can see we have a player, which is a point, or a position vector, a direction vector, and a camera vector. The length of the direction vector and the width of the camera vector give us the field of view. Within that field of view, we calculate the rays that intersect within the field of view and look for collisions and calculate the distance between our player and the collision point so we know how large to drive the object. When we want to rotate our player in a 3D raycasting game, we need to rotate the direction vector and the camera vector. We can multiply them by the rotation matrix, where A is the degree of rotation. We also need to rotate when we're casting rays within our field of view. Raycasting is not ray tracing. You may have heard the terms raycasting and ray tracing used interchangeably. Conceptually, they're similar, but from a practical perspective, they're different. Let's talk about how they're similar and different. For both, you need to calculate line intersections and lengths of rays. This is done using imaginary rays from the viewer's eye to the objects in the scene, and from the length of the rays, the size of the object on the screen is determined, so they both trace imaginary rays. With raycasting, because of geometric constraints, like keeping walls perpendicular to floors, it's only necessary to use one ray for every vertical column of pixels, whereas with ray tracing, you would cast a ray for every pixel on the screen. To summarize, the two big differences between the two are number of computations and quality of animation. Raycasting has fewer calculations and results in a simpler animation. Ray tracing has so many computations it's about 200 times slower than raycasting, but results in a hyper-realistic animation. Or to put it another way, you would use raycasting for a personal project game, but you wouldn't use ray tracing. Disney would use ray tracing. I have a link in the notes to a video of Disney using ray tracing in real time in 2018. Cool if you want to check it out, but we're going to move on now. Turn this into a 3D scene. This 2D array of numbers represents a 20 by 20 grid map with each non-zero value a block. The numbers can represent height or texture. In order to make it 3D, we need to calculate the distance from our player's location on the grid to each block and calculate the height of block based on the distance from it. So a further away block will be smaller on the screen and a closer block will be bigger. Let's look at some cool examples from the web. I'll walk you through the concept a little more and we'll come back here and get into the math. So, first we're going to look at a 3D game. You see the example right here. 3D games are the main use of raycasting. After this, we'll look at how raycasting is used in fun but slightly different ways in 2D. So for this 3D example, you can see this lovely 3D person experience implemented. So let's skip past the code and look at an illustration. In the first half of the illustration, you can see our player, the origin point, casting rays out at increasing angles along the field of view to look for intersections with walls. Then you can see the walls drawn as vertical columns with the height depending on the length of the ray. With more rays, you get a smoother result. In this next illustration, you can see a single ray being cast through a grid and getting checked at each x and y step throughout the grid. We'll talk more about this later with the DDA algorithm, but the point is to check at each of these steps if that square or spot in the 2D array contains a solid block. With this last illustration is an important detail for implementation. To avoid a fisheye effect, we need to multiply our distance by cosine of the angle from our player's direction vector to get the perpendicular distance to the wall. Now let's move on to our 2D example. Okay, so in this interactive example, you can see how I move my mouse around, and from the point my mouse is at, rays are cast down in 360 degrees as light beams until they intersect with a barrier and stop. This creates a flashlight-like effect. Now if we continue down the page, you can see how it is implemented first with just one ray and then with many rays. This programmer further improves the look of further improves the look until you end up with this resulting impressive example. But it all comes down to rays being casted out like this. Now let's go back here. Now, if you were paying attention, there is a slight difference between the math used in the 3D game example and the 2D game example. In a 3D game, you generally have a 2D tile map that contains texture information as well as whether it's a wall or not. In some games, in some 2D games, you have line segments or coordinates for the corners of the walls. If you have line segments, you don't have to check each tile to see if it's solid. You just check if your direction vector intersects any of the line segments. Let's look at this in detail. This is a formula from Wikipedia to solve for line intersections. With this formula, there are two steps: calculating the t and u to establish if there's an intersection, then if there is, calculating the exact point either using t or u. In the next slide, I'll explain where this formula came from. So that formula is just using variables from the points and simultaneously solving for each line using determinants. After you know that there's an intersection, then you can find the exact point using either t or u. For example, with x1, y1, using t, we know that x is x1 plus t times x2 minus x1, and y is y1 plus t times y2 minus y1. It's just change in x multiplied by the scalar factor t. So with that explanation, we can take a quick peek at that formula again. You can see, for example, looking at the numerator where we're solving for t, that it's just working out any two lines characterized by the points x1, y1, x2, y2, and x3, y3, x4, y4 using determinants like we've done in class. Once it's in the form of equation, it's very easy to get into code. When implementing a raycaster, the only difference for calculating a ray is that when you're using U to test if the ray intersects, the ray is not a segment, it's an infinite line with a beginning point. So the intersection has to be on the positive side of the ray. So long as U is greater than 0, we're good. and t has to be between 0 and 1 because it's a segment that begins and ends. Important note, the denominator for both t and u are the same. You only need to work it out once. Also, if you get 0 for the denominator, you know there's no intersection or the lines are laying on top of each other, so you don't need to do anything more. Let's take a minute to talk about how the DDA algorithm is used to decrease the number of checks that are necessary when looking for intersections in a 3D raycaster. Remember, with a raycaster, we have to check along the ray for collisions with walls. Well, some hacky and inefficient raycasters take tiny, equally sized incremental steps along the ray to check for intersections. The better raycasters take advantage of grid-based worlds and only check each side of each square by calculating the distance between steps and stopping once we reach a solid block. This is called digital differential analysis, or DDA. Basically, it's alternating between stepping by one tile along the x-axis and one tile along the y-axis and calculating the distance traveled along that ray in that step using the slope. So the basis of this algorithm is that you can calculate the length of C using Pythagorean's theorem, but if we assume a step length of 1 unit square, we can set either dx or dy to 1, and the other side becomes dy over dx. By putting those into the Pythagorean, we can calculate a scaling factor. We know the length if we've moved one step, so to get the length, we just multiply by how many steps in that direction. You can also see that sometimes the ray doesn't start on a tile corner, so to begin you must align the first cell. Since the tiles are seen as one, coordinates are a percentage of a tile, so you just have to manually calculate the length of the ray at the first intersection while being careful about direction. After that, you just keep adding 1 unit direction in whichever x or y length is shorter until you reach a collision. Giving line segment point vectors, player vectors, and a single player vector, and direction vector cast 3 ways, one straight ahead and the other 2 90 degrees in either direction. For each ray, determine if the ray hits a segment, write down which segment for which degree, or if it doesn't hit any, write none. Here we have our segments. First segment 2:12, 4:3. Second segment 6:6, 10:8. Third segment 5:18, 11:15. And our player is at 3:10, and the direction is -1/2, and square root of 3 over 2. These are the steps for each ray and line segment. So for our first step, we have to find all the points for x1, y1, x2, y2, x3, y3, x4, y4. So step 1 is easy. The first and second are easy. It's just the line segment we're checking. The third point is the player vector, and the fourth is the player vector plus the direction vector. And you multiply by the rotation matrix using the angle that you're casting the ray at, if it's not the same as the direction of the player. For the first ray, we're just adding the direction vector directly, but for the next one, we rotate by 90 degrees. The denominator, second step is calculate the denominator. The denominator for t and u are the same, so you only calculate it once. If it's 0, you're done and there's no intersection. The third step is to calculate t and u and check that t is between 0 and 1 and u is greater than 0. If it's not, you're done, there's no intersection. Our fourth step is to use either t or u to find the point of intersection. You only have to do this once with either t or u. in this case, I'm using an approximate decimal value for t. A computer would use a slightly more exact calculation. Okay, since we have 3 line segments to complete, I just run the same calculations on each line segment. Now I'll get the direction vector for my next ray using the rotation matrix to calculate it. Keep in mind, in code, you'd want a new variable for your ray direction vector because the ray calculations would not change the player's direction vector. These are the results that I got in working out the example for myself. I showed the calculations for the first segment with the first ray, and we got point at approximately 212, and the other segment 2 and 3 were no intersection because t was negative, and that's not between 0 and 1, so it's no intersection. And with the 90-degree rotation, none of them had intersections. With the first one and the third one, u was negative, and with t was negative for the first and third, and then with the second segment, u was negative, and so that also meant no intersection. You'll notice there are no intersections that intersect with the first rotation. That was on purpose. It made it quicker, so I didn't have to do as many calculations. The same idea for rotating the negative direction. Segment 2 is only the only segment that intersected. I worked these out by hand with a calculator as an exercise, but just doing a couple of them makes you very happy for the ability to program computers to do the calculations automatically for you. Thank you. That concludes my presentation. I hope you enjoyed it.